Hello everyone! If you've been paying attention to the indie game scene the past few years, it would be hard to miss the growing trend of graphics emulating the aesthetics of the PlayStation 1 era of games. A combination of several unique quirks of the PS1 GPU caused these games to have a dreamy, liminal, or uneasy appearance, which is very effective at inducing a powerful nostalgic feeling for minimal computational investment due to the old age of the techniques. So what were these quirks of the PS1 GPU? How are games today replicating that functionality on modern hardware? Is it worth the effort to try and make a game in this style? All this and more in today's video, where we make our own PlayStation 1 style scene. Released in 1994, the PlayStation 1 is the progenitor of many beloved series today, such as Crash Bandicoot, Spyro, Silent Hill, Persona, Bubsy 3D, and Resident Evil. When it comes to nostalgia baiting, it is one of these that you're probably going to try and emulate, so today we will analyze Silent Hill and try to deconstruct its visual components. Let's start by setting a scene. When I need some inspiration, I open my folder of random environment photos, which are all suspiciously similar now that I look at them. This image inspired me the most. I really like the bridge as a centerpiece of a dark, snowy environment, which would take full advantage of the foggy effects present in Silent Hill. I opened up Blender, modeled a bridge, sculpted some terrain, and used a flat plane intersecting with the terrain to represent the river for now. After importing my models into Godot, we have a blank scene ready to apply our PS1 effects to. The first thing I would like to do is apply some textures to our models to get some color and details. So how did the PlayStation 1 handle textures? Given its hardware from the 90s, the PS1 has some significant memory limitations, making high-resolution textures an impossibility. The PS1 comes with a whopping 1 megabyte of VRAM, meaning all of the space available could be contained in a single 1024 by 512 16-bit texture. This is not a lot of space, and even worse, the texture presented to the screen so we can actually see the game after it's rendered takes up some of this space as well. The largest texture the PS1 could write to is 640 by 480, making that the highest resolution a PS1 game could technically be rendered at. In practice, PS1 games would divide this texture into two, making use of a double buffer setup such that one texture is presented to the screen while the other is rendered to, preventing any flickering from GPU latency and significantly improving the frame rate because rendering at quarter resolution is always much faster. From my research, the actual target resolution of PS1 games varied greatly. Spyro is rendered at 297 by 217, Silent Hill is rendered at 319 by 223, and Metal Gear Solid is rendered at 320 by 200. So to be historically accurate, any target resolution less than 320 by 240 is fine, but it is 2025, and you could technically do 640 by 480 if you really wanted to. Since we're copying Silent Hill today, I'll be rendering at 319 by 223. Given the implicit double buffer setup that we'd technically be using if this were the 90s, leaves us with about 480 kilobytes of VRAM per scene, which is like a 704 by 512 texture. While the largest texture a PS1 could write to is 640 by 480, this is not the same when it comes to reading, and the largest texture we can use for polygons in the scene is 256 by 256. With our limited VRAM, that gives us about 4 of those to work with for everything we want to render in a scene. This means we want to be as efficient with our textures as possible, as demonstrated here by some Silent Hill textures that I ripped from the game. As you can see, many different surfaces are packed into the small space available. Applying these observations to our own scene, I painted a small, snowy 256 by 64 texture in Photoshop by layering some noise textures. Given the small scope of our scene, we could be much greedier with our textures here to give more variety, but I ended up using this one texture for both of the bridge and the terrain to keep it simple. Low-resolution render targets and textures already gives our scene that retro feel, but our modern GPU is actually doing something behind the scenes that's preventing it from looking exactly like the PS1 did. The GPUs of today account for perspective when sampling textures, while the PS1 GPU did not do this, instead utilizing a technique called Affine texture mapping. To understand what this means though, we first must learn about how we go from a polygon in the scene to pixels on your screen. Imagine A cube. The points or vertices that make up this cube are defined relative to the cube's origin, the center of the cube. For example, 1, 1, 1, negative 1, 1, 1, etc. We would say that these positions are in local space, local to our cube 3D model. Now, imagine that this cube exists in a greater world in some arbitrary location. Positions here are defined relative to the world's origin, not the cube's. If our cube was 5 meters to the right, then our 1, 1, 1 position would no longer be accurate. It should be 6, 1, 1. We would say this position is now in world space. To go from local space to world space, we use something called a model matrix, which is a transformation matrix that, when multiplied with a vertex position, transforms it into its position in the world. In this example, our model matrix would be a translation 5 units on the x-axis. For a deeper explanation of transformation matrices, please check out my video on procedural particle fractals. When we move objects around in a game engine editor, we are modifying the underlying model matrix, not the actual vertex data of the object. Now, imagine a camera pointing at our cube. We would like to know where this cube is in relation to the camera, with the camera being the origin of this new space, which we call camera space or view space. If we imagine a set of axes laid over our camera, then the direction of our camera will always represent the direction of the positive z-axis. With this camera direction, we take the cross product with a vector pointing up in world space to obtain the direction of the positive x-axis. Then finally, we take the cross product of the z and x directions to obtain the positive y direction of the camera, and we have the axes of our camera space. Since we have a coordinate space defined by 3 axes, we can convert any position to it by simply multiplying by a matrix containing the 3 vectors, and to account for the position of the camera, we also multiply by a translation matrix. This transformation matrix is called the view matrix, and when multiplied with our world space cube position, gives us the position of the cube relative to the camera. We still have one more coordinate conversion left, but at this point, we should talk about what the GPU actually expects to receive in the end. When all is said and done, our position should be in the range of -1 to 1 if we want it to be on screen. This range is known as normalized device coordinates. Anything outside of this range will be discarded or clipped, and so our final coordinate system is known as clip space. The conversion from view space to clip space is known as projection. There are 2 kinds of projection matrices, orthographic and perspective. For 3D, we want perspective projection for actual perceptual depth in our scene. The construction of our perspective projection matrix starts with defining the 6 planes that form our camera's frustum. Any point inside this truncated pyramid will be within view of the camera. Generally though, frustums are symmetrical, and so we only need to define 3 values: the horizontal field of view angle and the distance of the near and far planes of the frustum from the camera. We take the tangent of half the field of view angle and multiply with the distance of the near plane to get the left and right of the frustum, then multiply one of those by the aspect ratio of the screen to get the top and bottom of the frustum. From here, the actual derivation of the projection matrix is considerably complicated, so if you're mathy, you can read this article that explains it in detail. The 6 values come together to form this matrix. The perspective projection matrix transforms our truncated pyramid slice of view space to the normalized device coordinate range cube. Any position in view space that is outside of the frustum is discarded because it'll be outside of the -1 to 1 range upon transformation. In summary, our vertex positions start out relative to the 3D model that they make up, which we multiply by the model matrix to transform to world space, which we multiply by the view matrix, so we transform to view space, which we multiply by the projection matrix to transform to clip space. While we might have these concepts of a world or a camera as actual things, they are, in reality, just transformation matrices behind the scenes. After our polygons have been converted to clip space, they're sent off to the rasterization stage of the rendering pipeline, where it's converted to pixels on your screen. And it's at this point where the PS1 GPU and modern GPUs diverge. Okay, there is just one more step of our model view projection transformation. Clip space coordinates are actually 4-dimensional. The projection matrix grows the 4th component W based on the distance from the camera, and the 3 other components are in the range -W to W. To finish our conversion to the -1 to 1 range, we divide the X, Y, and Z components by W. Since W grows based on distance, the further an object is from the camera, camera, the tinier it becomes, simulating the perspective effect of distant objects appearing smaller. This final step is called perspective division, and modern GPUs do this for you automatically because they are built for 3D rendering. It might surprise you to hear this after talking about 3D PS1 games so much, but the PS1 GPU is actually a 2D renderer. Any clip space position passed to the PS1 GPU has its third component discarded, and it only works with the X and Y coordinates of the 2D plane we projected our vertices onto. Because of the magic of the model view projection matrix transformation, PS1 games could be 3D despite the fact it's a 2D rendering engine. But how does this limitation affect the final appearance of the scene? After our clip space positions have been finalized, the rendering pipeline moves into the rasterization stage where our polygon is converted into pixels. It's here where yet another important quirk of the PS1 GPU appears. It works with integer values only. Our clip space coordinates are rounded to the nearest whole number. Modern GPUs can use that decimal value for sub-pixel rasterization, providing smoother motion as polygons cross pixel boundaries. But on the PS1, a pixel is either occupied or not. No partial occupation is allowed, resulting in pixels flickering on or off, giving the iconic wobbly appearance to objects that move very slightly. After pixel occupation is determined, the vertex data is linearly interpolated across the pixels based on the 2D screen coordinates. But uh-oh, because of our perspective correction and 3D shenanigans, the vertex data now has a non-linear relationship with the 2D screen coordinates, causing incorrect interpolation results and distorted textures. As I mentioned earlier, this technique is called affine texture mapping, and it is probably the most defining characteristic of PS1 graphics. Modern GPUs do not have this issue as they are able to properly interpolate perspective correct values because they're actually meant to render 3D scenes, unlike the PS1, which is why our scene currently doesn't have this distortion. While the overall 3D rendering process is pretty much the same today as it was on the PS1, the integer coordinate restriction and affine texture mapping give the PS1 its unique wobbly and distorted appearance. Now that we understand how this all works, it's time to implement and apply it to our scene to see the difference. Let's start by rounding our pixels to simulate the wobbly nature of PS1 graphics. The rounding occurs when the clip space vertex position is passed to the rasterizer on the PS1, so we want to modify our clip space calculation in the vertex shader. Our vertex starts out in local space, which we transform to world space, then view space, then clip space. Remember that clip space positions are in the range -W to W, but if we want to round to the nearest point on the pixel grid, we need to convert to the range of our screen resolution. We divide by W to convert to the -1 to 1 range, multiply by our screen resolution, round the result, then divide by the screen resolution to return to the -1 to 1 range, and multiply by W to return to the -W to W range because the GPU will automatically divide by W later for us. This results in vertex positions rounding to the nearest exact pixel coordinate on screen, and no more partial occupation of a pixel can occur, preventing our GPU from doing any sub-pixel rasterization and simulating the PS1 pixel snapping. Remember that this effect is only super obvious when objects are moving very slightly at a low resolution, otherwise it looks pretty much the same. Now to introduce the PS1's distorted textures, we need to undo the perspective correction that our GPU does for us automatically. We multiply our vertex UV coordinates by W, and then in the fragment shader, we divide by W to reverse the perspective correction applied during interpolation, then sample our texture. Pretty simple. Here's a comparison between the two. As you can see, the distortion is really bad here. It almost seems wrong, because if you've played PS1 games, you probably never saw anything like this. So how did PS1 developers hide severe distortion from the players? The distortion gets really bad when polygons are viewed at even mildly grazing angles, so an easy fix for this is preventing grazing angles from ever occurring by disallowing players from controlling the camera. Fixed cameras were very popular in the PS1 era. Silent Hill, Resident Evil, and Metal Gear Solid all make use of fixed cameras that generally prevented grazing angles. Other games like Wipeout or first-person shooters like Alien did not have this luxury though, and instead had to make use of another solution. The other case in which heavy distortion occurs is when the polygon takes up a lot of space on the screen, so to fix this, we need more polygons. If we subdivide our cube to contain more triangles, the distortion pretty much entirely disappears as less data needs to be interpolated and less error accumulates. It might be surprising to hear, but the PS1 took heavy advantage of real-time quad subdivision so that that the geometry would be much more dense, closer to the camera, preventing any severe distortion. This was possible because the PS1 drew polygons one at a time from CPU commands, so the CPU could very easily draw more polygons if needed. We could simulate this on modern GPUs through the use of tessellation shaders, which will subdivide meshes for us at runtime based on view distance, but nowadays, this distortion is less of an undesirable artifact and more of an intentional feature, so I chose not to do this because the tessellation shaders would fix the distortion almost entirely. With pixel snapping and affine texture mapping, our scene is looking a lot more accurate to the PS1 era. It's looking a little flat though because there's no lighting or shadows whatsoever. So it's time to learn about how PS1 games did lighting. I've covered lighting numerous times in my videos at this point, and it's always been pretty involved because in the modern era, we can make a shader do whatever complex behaviors we want through shader code. But in the PS1 era, programmable shaders did not exist. In fact, programmable shaders weren't a thing on consoles until the PS3 and Xbox 360 era. This is great news for people who want to make a PS1 style game, because technically writing any shader code at all is against the rules. Obviously, we have to write some shader code to reverse the conveniences of modern GPUs, but when it comes to lighting, things have never been simpler. The PS1 GPU has what's known as a fixed function architecture, meaning it does exactly what it's built to do and cannot be reprogrammed to behave differently. The PS1 GPU could draw triangles as well as quads, unlike the GPUs of today which only draw triangles, and these polygons could be flat shaded, textured, or Gouraud shaded. This third option, Gouraud shading, is where PS1 lighting comes from. When vertices are passed into the GPU, they can come attached with something called a vertex color, which is then interpolated across the pixels during rasterization, just like our UV coordinates from earlier. These vertex colors don't really have to be colors though. We can interpret that data however we want, such as treating it like light data. If each vertex stored a brightness value, then during interpolation, lighting is achieved as this brightness is smoothly blended across the polygons. This technique is often referred to as vertex lighting, and I think that's because people just don't know how to pronounce Gouraud shading. Since only one value can be stored per vertex, we are limited to a single light source, whether that be a directional light, point light, spotlight, ambient light, or whatever. We only get one. Most games would use this channel for ambient occlusion to give some sense of shadowing in the scene, but Silent Hill actually saves this channel for the flashlight and communicates ambient lighting through the color textures. I don't feel like programming a flashlight, so I just went with the usual ambient occlusion since my texturing doesn't take lighting into account. In Blender, I manually painted the ambient occlusion onto the vertices, and when imported into Godot, we multiply the vertex color with the texture sample in order to get our lighting. Remember that because these vertex colors are interpolated across the screen, the Gouraud shading on the PS1 is also perspectively incorrect, and so we must reverse the perspective correction using the same trick we did to the UVs, although it's nearly impossible to actually see the distortion anyways. With lighting baked onto our model's vertices, our scene looks much less flat, which is great. Now, for probably the most exciting part of the video, it's time to dissect and learn about one of the most famous effects of the PS1 era, the Silent Hill fog. It took me quite a lot of digging on the internet to find an actual explanation for how Silent Hill fog worked, and even then, I didn't really get an answer. So I pulled up an of Silent Hill and used NVIDIA Insight to capture a frame to get some idea of what's going on. Remember that all of the PS1 VRAM is contained in a single small texture, so on the left we have that double buffer setup with one of them being rendered to while the other is presented to the screen, and on the right we have all of the textures currently in use. As you can see, the PS1 really does draw the scene quad by quad, but interestingly, we're seeing two quads drawn each time. First, a black Gouraud shaded quad, and then the textured quad is drawn on top. The developers of Silent Hill are doing quite the dastardly trick here to get high quality fog into the game. This first quad that is drawn is actually the fog shaded quad, with the vertex color of each quad containing not lighting information, but the fog factor. The PS1 GPU then blends these fog factors together during interpolation, giving us the fog gradient into the distance. This means the fog is also distorted by the lack of perspective correction. But what about the textured quad? This quad is actually semi-transparent, such that it blends with the underlying fogged quad, otherwise it would just completely cover up the fog. The end result is what we know and love, simple yet effective distance fog, but it doesn't come for free. It's actually really expensive. Since two quads are drawn per quad, this doubles the geometry count of the scene, which is why the fog is so intense. Silent Hill really couldn't afford to render that many polygons with this heavy of a restriction, and would use the fog to hide all of the stuff not being rendered in the distance. According to the technical specification, the PS1 could handle up to 90,000 polygons polygons on the screen with texturing and Gouraud shading enabled, so Silent Hill could only do 45K, and even then, I'm not sure if that is for 30 FPS or not. Obviously, it is 2025, and this is not really a concern for us since GPUs can handle millions of triangles with ease now, but it was certainly a headache for the developers of Silent Hill. Recreating this fog effect for ourselves is quite simple. For each vertex, we calculate the distance from the camera, send it through a linear fog factor conversion, invert it so that it goes from 0 to 1, and blend between the pixel color and desired fog color. No need to draw the polygons twice. The result is a beautiful, moody, foggy scene. How pleasant. Our scene is very nearly finished, but we're still missing one of the most crucial components of the PS1 era, dithering. In the current day, monitors and games can output and handle an extremely high amount of colors, with 24 bits being used per pixel on your screen, supporting 16.7 million different possible colors. In the 90s though, this was not the case, and colors were more often 15-bit, supporting only around 33,000 possible colors. While the PS1 did process 24-bit color during rendering, it still outputs 15-bit color. With such a limited range of colors, gradients didn't look so good, and would often contain an artifact known as color banding, where there are visible abrupt changes between the colors. In a game like Silent Hill, this color banding would be very apparent due to the fog introducing a gradient. We can actually see this banding in the I'm using because it has disabled the dithering. Currently our scene is rendering 24-bit colors, so it looks totally fine, but we want to reduce these 16.7 million possible colors to 33,000. We do this with a process called Quantization. 8 bits per channel means 256 possible values, including 0, so we multiply our color by 255 to put it in that range. In 15-bit color, there is 5 bits per channel, meaning 32 possible values, so we divide our color by 8 to reduce the range to 0 to 31, and we have 15-bit color. This quantization introduces some pretty gnarly color banding, especially on the river. To fix this, we use something called dithering. Dithering is a technique where we intentionally add noise to the image in order to spread gradients out and create the illusion of a smoother blend. In the past, I have covered Bayer dithering and blue noise dithering, most famously used by the game Return of the Obra Dinn, but the PS1 actually had its own proprietary dither matrix. This 4x4 matrix is tiled across the image, and we use the screen coordinate to index the matrix and grab its corresponding noise value, which we add to the color before reducing to 15 bits. The result is a pleasantly dithered image, and we now have that iconic washed out PS1 dither appearance. Due to the lower resolution and upscaling, the dither pattern is very obvious, but this is how it was back in the day, so... You can see that the PS1 dither pattern has an almost scanline-like appearance, which, given the use of CRTs back then, this would probably look a lot cooler on a CRT. At this point, we have covered pretty much everything that goes into the PS1 aesthetic, so it's time to finish up our scene with some particles, sounds, and music. Given the geometry limit of around 90k polygons on screen at one time for the PS1, our scene is well within that limit at only 20k, which is kind of a lot I guess, but even if we were doing Silent Hill's double geometry, we'd be okay. Silent Hill also features some particles that drift down. Whether this is snow or ash, who knows? But given our snowy scene, I thought some snow particles would look great, as we have plenty of available polygons to work with. While I usually roll my own systems, for this I just used Godot's built-in particle system because particle systems are not the topic of this video. Go watch this other video for that. We create a particle emitter sitting above the camera that shoots out some quads at slightly random angles and velocities, and we have snow. I was satisfied with the appearance of the scene at this point. I was originally going to do something for the river to give some detail, but given the low resolution and suffocating fog, the dither gradient already provides some texture to the river, and I didn't think anything more was needed. Whether it's dimly lit ice or water, who knows? Next, I used Audacity to generate some noise for ambiance that sounds like this. The scene feels like it would be quite stormy or windy, so the noise helps with the audio-visual cue. Then I used BFXR to create a simple footstep sound, which is also just noise, but I think it sounds good enough. Lastly, I wanted to put my piano skills to use, so I learned the first few measures of one of my favorite songs, Pavon OP50, which I think matches the overall vibe, and our little PS1 scene is finished. If you want to make a historically accurate PS1 game, then your project should be rendered at or less than 320 by 240, have no more than 90k textured and shaded polygons on screen, use no more than around 424 kilobytes of VRAM for textures, one light source, perspective incorrect interpolation, clip space rounding, 15-bit colors, and dithering. If your goal is to simply capture the essence of the PS1 era, then what matters most is the incorrect interpolation and clip space rounding. The other limitations are really quite arbitrary. No one is going to count the polygons on screen or check to see you're not using very many textures. With all this in mind, I think the PSX aesthetic is really quite accessible even for beginners. All of the topics presented in this video amounts to only a couple lines of shader code. Beyond that, it's your art and game design skills that matter most. If you're interested in a new PS1 style game to play, this video and topic was brought to you by my friend Mr. The and Street Uni X, the world's first authentic street unicycling video game featuring the most hardcore, radical tricks you've ever seen. Street Uni X applies many of the topics covered in this video to present an authentic retro experience, taking real-life locations and demaking them into the visuals of the 90s. Unlike the games I make for my videos, Street Uni X is actually tons of fun to play, especially if you're a fan of other arcade skating games like Tony Hawk. With unique controls that capture the nuanced capabilities of unicycling, alongside the nostalgic, goal-oriented gameplay rush of extreme sports video games past, Street Uni X will leave you at the edge of your seat while you wall tap to your next grind. So be sure to check out the game's free demo on Steam linked in the description. I'd appreciate it a lot. Thanks so much to Mr. The and Street Uni X for sponsoring this video. Overall, it's pretty obvious why the PS1 aesthetic has grown in popularity over the years. Its simplicity and nostalgic appearance makes it a great option for indie developers, and I sure do love dithering. The only thing I really didn't talk about in this video is the PS1's quirky Z-fighting, which is really hard to replicate given it was an artifact of the PS1's software renderer approach, and if I were to recreate it, it'd be extremely slow and not really worth the effort. Maybe I'll do it for a future video. If you'd like to support the channel and help me continue creating free graphics programming resources, please check out the Patreon. While the code for this project is available for you to build in the description with comments explaining the shader code, patrons get access to a build of the game so you don't have to build it yourself. So if you want to walk around in my snowy scene, you can find it over there. As usual, a huge thank you to all my current patrons. Without your support, I wouldn't be able to spend all of your money on Minecraft IMAX tickets. Also, I'll be giving a talk at GodotCon next week, so if you're around, come say hi. Anyways, that's all from me. I hope you have a great rest of your day, and I'll see you next time.